Welcome to SingleCrystal 5. In this tutorial, we'll show how to calibrate your observed electron diffraction pattern so it shows the correct scale and matches up with your simulated patterns. Now, why do we need to calibrate? The problem is that most TEM control software these days does not embed the correct resolution in output images, and usually a generic and bogus value is used. So how do we work around this? Well, there are three approaches you can take. First of all, you can tell the program what the correct resolution actually is. If you don't know the correct resolution, well, in that case, you could use an embedded scale bar in your image as your reference. If you don't even have an embedded scale bar, then you'll need to use a reference pattern. We're going to take each of these examples in turn. So I'm going to launch SingleCrystal and I'm going to create a new window. And the important thing to do is to start off by defining what kind of simulation you want to create. So I want a TM diffraction pattern, and I want to set the wavelength or the voltage. So I've got 100 kilovolts electrons, that sounds fine, and the camera length. Now the camera length is important. That is the distance from the electron source to your screen or your piece of film, your recording medium, and the further away you are, then the more magnification you get. Now, many people don't know the camera length because their microscope is a black box, but it's something that your manufacturer should be able to tell you. Typical lengths are around 1 meter. Now, in my case, my film was recorded in the 1980s on an old AEG electron microscope whose camera length was a bit shorter, about 44 centimeters. So let's enter that, and you can see that our little circle has got smaller. And now we'll take our observed pattern and we're going to drag and drop it into the diffraction window. And we have an overlay scale bar. Now this will be meaningless at the moment because we haven't calibrated our pattern, but I'm going to set the units to reciprocal angstroms for the moment. Let's have some fun coloring so that our observed pattern is easier to see. And then we'll go to the resolution group of the picture inspector, and you can see that the resolution can be defined in terms of 3 different parameters. So the simplest to understand is the physical size of this image. If it was recorded on film, then you would have a physical medium which you could measure with a ruler, and you could put in the exact size of that image. These days things are a little bit more hidden away and you don't necessarily know how big your sensor is. The pixel density, if you know the resolution, perhaps you scanned a film, you might have used 300 dots per inch or 600 dots per inch or 1200 dots per inch, you could enter that there as well. And finally, the pixel pitch is the distance between the individual picture elements of your sensor. And that's something that your manufacturer will publish. Now, in our case, I scanned this film and I used a resolution of 1200 dots per inch. So I can enter that into the pixel density and hit return. And there is my image. Let's auto scale that. And now we have got the correct size. Just check that you're using the correct units, in my case pixels per inch. Note that we do have some slider buttons here, so if you want to, you can experiment with zooming your pattern by dragging the sliders and seeing how the difference in resolution affects the size of the image. Is this correct? Well, let's compare that with a simulated pattern for the same material. So I'm going to drag and drop a crystal structure into my diffraction pane. Here is a simulated pattern, and let's overlay this onto the observed pattern, and you can see that the spacings match up quite nicely. This is the preferred method for calibrating your pattern. If your pattern has an unknown size or resolution, but it does include an embedded scale bar, then you can use this to calibrate SingleCrystal. Let's set up our simulation again, and it's a TM diffraction pattern with 100 kilovolt electrons and a 44.4 centimeter camera length. Let us load in our observed diffraction pattern, and let's auto scale that, and we can see that we have an observed scale bar there. Now let's set our simulation units to reciprocal angstroms to match, and you can see that our observed scale bar, which is about the same length as the overlay, but it doesn't quite match up in terms of measured units, so we need to calibrate this. Let's just move this back over. Now we can use the magnify tool to zoom up around a region of your pattern, and I'm going to use the ruler overlay to measure the size of my observed scale bar. Let's make our ruler a little bit less transparent. So using our current simulation parameters, our ruler is measuring about 4 reciprocal angstroms across, but we want it to be about 0.5. Now when the ruler is selected like this, you will have a ruler inspector on the right hand side, and there is a calibrate experiment button here. So let's click that. And now we've got a choice of calibrating the picture resolution or the camera length. Now we've already defined the camera length. We know the camera length, so we don't need to define that. But what we don't know is the picture resolution. So that's what we need to define. And it's saying the distance on the ruler, as we've seen, was about 4 reciprocal angstroms, and it wants to know what the true distance is. Well, we know the true distance should be 0.5 reciprocal angstroms. So let's click OK. And now the picture has been zoomed, so we're going to auto scale. Let's hide the ruler. And we need to recenter the picture. And now you can see that our scale bar matches the simulation scale bar exactly. Okay, that's the theory. Did it work? Well, let's take our crystal structure for this material and we'll load it in, and we can compare the crystal structure, the diffraction pattern from the crystal structure, with our observed pattern. And I'm going to take my observed pattern and we can just emphasize the diffraction a bit more clearly. Let's see if we can accentuate our spots a bit more. There we go. And we can maybe change the gamma level a little bit so it stands out a bit more. And this is my simulated pattern, which I'm going to color in red. And yes, the spacings match up. If you don't know the scale of your pattern and you don't have an embedded scale bar, we've said you'll need some kind of reference. And here is an example where that is indeed needed. Here we have an observed TEM diffraction pattern recorded from a crushed crystal grain that was mounted on a carbon film. And I think you can see that the crystal is giving us some nice, reasonably sharp spots, given that it was a crushed grain. But we also have these amorphous rings essentially powder rings that come from the carbon fill. And we can use those as a reference because their despacings are known. Let's load this into SingleCrystal for a closer look. Again, we'll check that we're simulating a TM diffraction pattern, that we have the correct wavelength or voltage, and that the camera length is set. Critical parameters. Let's drag and drop our observed pattern into the window. Let's auto scale that, and let's just check it's centered. It's slightly off center. I can use the center on max intensity command to center on the 000 spot. And while we're at it, let's change our distance units to reciprocal angstroms. Now we can measure distances on our pattern using the ruler, or also using the arrow tool. And the arrow tool shows us the distance of the arrow from the center of the pattern, and it gives us the corresponding distance in whatever the screen units are, which are currently reciprocal angstroms. And we can use that to get a rough idea of these powder rings. So the first powder ring is approximately 0.4 reciprocal angstroms. That's about 2 real angstroms. And the second powder ring is approximately 0.8 reciprocal angstroms, or 1.2 angstroms despacing. And those seem to match up pretty well with the published despacings for amorphous carbon, which are 1.2 angstroms, 2 angstroms, and there should also be a ring at around 3.5 angstroms, which I don't think we're seeing. So it looks as if in this case this pattern is actually correctly calibrated. If it weren't correctly calibrated, we would use the same procedure as in the previous example. We would display our ruler, we would measure the radius of one of our powder rings, so 0.87 reciprocal angstroms, and we would use the calibrate experiment command, and we would type in whatever the reciprocal of that powder ring is. This is actually the 1.2 angstrom powder ring, so the reciprocal is about 0.86. So we don't need to calibrate this, but this is the procedure that you would need to use. Let's just summarize what we've found. You do need to calibrate your observed pattern. That is essential. You cannot rely on modern TM software, and if you have a physical fill, then you have no choice. There are 3 ways of calibrating. You either have a known resolution that you can enter into the resolution group of the picture inspector, or you can use an embedded scale bar, zoom it up, and use the ruler to calibrate that by clicking the Calibrate Experiment button. Or you can use a reference pattern which you can measure, again using the ruler tool and the Calibrate Experiment button. That should give you a great basis both for measuring your observed data and, in combination with a crystal structure, for auto-indexing. We hope you found this useful.